my name is Zico Coulter. I'm a faculty member in computer science, and I'm going to be guest lecturing today for Ryan. I think I know some of you, but not that many of you, so it's good to meet everyone here. Before we start today, I do want to take a moment to mention the events over this past weekend. I know Ryan wishes he could be here to address the class. It's somewhat odd that I don't know many of you, but I do think it's important that faculty speak to students to let them know that they're here for you, and that we as a community are here for each other. Things like this are, of course, they're attacks on the entire Jewish community, but they're also very personal attacks on our city and our university. As one example, Steven Feinberg, who was a faculty member here in Stats, passed away 2 years ago now. He was one of the founders of the machine learning department. And his widow, Joyce, was one of the victims of the attack. And many of you also may know people who are either, you may know some of the victims, or you may be connected to them somehow. And just personally, Squirrel Hill is my home. I've lived there for the past 6 years. And this is going to sort of stick with us for a very, very long time. But to echo something that I hope is, you've probably heard a lot over the past few days, is I hope that what really sort of shines through in these times is not, and what defines us as a community is not the attack itself, but the way we respond to it and the love and support we give each other in times like this. So with that in mind, I did want to take a moment at the beginning of the class to just, this is a slide that Jonathan Aldrich prepared as sort of a way of commemorating the victims and pointing out some things you can do. But I also want to just have a moment of silence for the victims of this attack. Okay, so I do want to highlight the things that he mentioned in the slide, things you can do to support. I know these are minor things in the grand scheme of it, but first of all, supporting one another and recognizing the impact this has, especially in the Jewish community. Speak and espouse tolerance and respect for all ideas, lifestyles, and religions. More concretely, in times like this, people want to do something, and donating blood is something that can be done. That's always useful. There also are some various funding pages for the Tree of Life synagogue in Squirrel Hill. The last thing I'll say is that if you do want to talk with anyone about this, both myself, Ryan, you're welcome to just email us, but there's also counseling available at CMU. I think the link has been sent to everyone, and the emails have been communicated to everyone. But I hope if you do feel the need to reach out, you're comfortable doing so, and you're encouraged to do so. So with that in mind, we are going to continue the class as normal. But I just want to say this in the beginning to make sure that everyone knows that this is not a small thing. This is a major event that's happened, and the resources are here, and we are here for you and for each other. So thank you. Okay, so. Jumping in now to the topic at hand today. Today's lecture is going to be about quasi-Newton methods. And I guess last time in class, we have these reviews of, Ryan had these reviews of the last lectures for class each time. So last time we talked about primal dual interior point methods. And these, I would say, are sort of, the idea here is you have some constrained optimization problem, convex constrained optimization problem, and you have some residual which approximates the KKT conditions of that optimization problem plus a little additional central path term here. And you take this term eventually to infinity, the t to infinity, as you progress along the path. And the idea of primal dual interior point methods are that you essentially use Newton's method to find a zero of these equations, right? And so that looks like this. You basically update your parameters, both your primal and dual parameters, based upon the Newton update for this system here, which is given by the following equations. And the ideas here is that these maintain iterates that are not necessarily feasible, but as you converge, they become feasible, both for the inequality and the quality constraints. And this really is the state of the art in exact solutions to not large scale, to sort of medium scale convex optimization problems. And historically, I really think that this was sort of a breakthrough that's often unappreciated right now, in that we kind of take it for granted that you can solve medium scale semi-definite programs. Of course you can, and things like this that 20 years ago were not at all things you could just solve, right? This was sort of a mathematical formulation that was very hard to make practical. And these sort of tools have really made these things practical, at least for small scale problems. We complain now that these things are not fast enough on large problems, but really this is an amazing sort of technology that lets us solve them to begin with. And so with that kind of as context, this lecture is really about another such technology we kind of take for granted in a certain respect, I think, which are quasi-Newton methods. So in the lecture today, we're going to talk about quasi-Newton methods. And in particular, we're going to talk about the SR1 and BFGS methods. I'll also mention the DFP and the Broyden class of algorithms. We'll talk about their convergence very, very briefly. I won't actually prove convergence. I'll just mention what the convergence result actually is. Hopefully you can sort of understand what these results are. And then I'll talk about limited memory BFGS, or sometimes called LBFGS, which is actually also one of the kind of workhorses of modern convex optimization. And finally, I'll just mention at the very end some sort of current recent work on stochastic quasi-Newton methods. This is something I actually know much less about, and I think the jury's still out on whether these things will really supplant things like just normal SGD for a lot of problems. But I think it's worth highlighting at least that there are stochastic variants of these things that are applied in similar ways. So of course, feel free to stop me at any point if you have questions. I can answer them to the best of my ability. All right, so let's just jump right in. And to take a step back now, we are back in the realm now of unconstrained, smooth optimization, convex optimization. So, for interior point methods, we talked about, or Ryan at least, had talked about constrained optimization, right? You have inequality and inequality constraints. And now we're back in the realm of, for now, unconstrained optimization. So we're just trying to minimize some function, f of x, with no constraints. And we assume f is convex, twice differentiable. Well, can't be twice differentiable, but it is smooth. And so, the gradient descent update is just you update x by taking a small step in the direction of its negative gradient here. Newton's method, if you remember, was an alternative update we could do to optimize f. And the idea here is very similar, except that instead of optimizing it in the direction of the negative gradient, we optimize it in the direction of the Hessian inverse times the gradient, right? Times some step size as well, some step size t. And this was nice for a variety of reasons that we talked about, or that the class covered before. It has, at least locally, it has quadratic convergence, meaning that once you get close to the optimum, you get accurate to numerical precision really, really quickly. So essentially, it's solved to numerical precision once you get close enough to the optimum. The problem, though, is that Newton methods are expensive, right? We'll talk about that in a little bit more detail in a second. But really the problem here, of course, is that Newton methods have two big problems. The first problem with Newton method is you have to first compute the Hessian to begin with, right? The Hessian is an n by n matrix. If n is really big, maybe you can't even compute it to begin with, right? Maybe it's just too big to even store. And secondly, you have to solve the Hessian system. That is, the Hessian times your update, delta x, equals the negative gradient. You have to find a solution to that linear system of equations. And if the Hessian is an n by n matrix, in general, if these are all dense, computing that update is going to be an n cubed operation, right? So that could be, compare that to gradient descent, which is just a order n operation to update everything. That can be a pretty costly operation to actually go about doing. So what quasi-Newton methods are, our quasi-Newton methods are kind of something in between these two extremes of just gradient descent for the simplest update you could have, and Newton's method for a much more complex update, which gives much better convergence. As we'll see, they actually have convergence that looks a little bit more like Newton's method, but without all the computational costs of Newton's method. And this is really, I think, one of the, like interior point methods, this kind of idea is one of the big breakthroughs of optimization. Again, not recently, because this is quite old technology now, but it's really been a breakthrough in how we practically solve optimization problems. So the basic idea is actually quite simple. We're going to update x here in the, I might just point to this just to have some cursor here. There we go. That's not very good. Oops. Let's get back. OK. We're going to update x to be x plus some step size times some direction delta x, right? Just like in Newton's method. But whereas in Newton's method, this delta x was the actual solution to that system of equations above, here we're going to solve a different system. The system we're going to solve is b times delta x equals the negative gradient, where b here is some kind of approximation to the Hessian. All right? And I'm not saying what it is yet. In fact, different methods will use different approximations to the Hessian, of course. But the idea is we want b to have two properties. We want it to be easy to compute or represent. And secondly, we want this system of equations to be easy to solve. Okay? And quasi-Newton methods are going to sort of address these 2 points. And just as a preview, maybe I'll sort of mention this here. So if you have the sort of the spectrum of Newton methods, Newton's method, which is going to be really order n cubed in the worst case, because you have to solve that linear system, which takes n cubed time. And then gradient descent over here. Which is order n. Quasi-Newton are kind of in here. And just as a preview, they are going to be order n squared for exact quasi-Newton methods. But they seem to be, despite being n squared, they seem to work better than Newton's method at achieving numerical precision, accuracy, without needing n times more steps. So each step is n squared, as opposed to an n cubed step with quasi-Newton, but they seem to be therefore just kind of faster because they don't require n times as many steps to actually converge. But we'll see that in a second, but this is just sort of a preview about where we're going. And then there's actually going to be a thing that lies in between here, which is the limited memory. Quasi-Newton. And that's going to be actually order n, or some small constant times n. We're not actually going to have the guarantees of quasi-Newton methods. It's not a true quasi-Newton method, but it actually gets some of the benefits still of quasi-Newton methods. So this is kind of an outline for the complexities we're going to talk about in the course today. OK, so what is this matrix B that we're going to use here, and how do we form it, maintain it, and solve it? That's going to be the question we're going to deal with today. First of all, there's some history. So actually, there's a really interesting history behind quasi-Newton methods. This guy, William Davidson, he was actually a physicist mainly, but also a mathematician at Argonne National Lab. In the 1950s, he developed quasi-Newton methods. And it's kind of funny. He supposedly, the reason why he developed them was he was trying to optimize some function with coordinate descent. And this being the 1950s and computers being what they were at the time, the computer kept crashing before he could finish his computation to actually optimize the equation. So his solution to this was to develop a mathematically better algorithm so that it would converge faster and therefore could run more iterations and get a better solution before the computer inevitably crashed when he ran it. And soon other people sort of started building on this work, and actually one of the algorithms we'll talk about, which is the DFP method, was the work of Davidson, Fletcher, and Powell. Now, although this was a sort of a major breakthrough in the field, so mathematically, right, it actually he couldn't get his paper published for a very long time. So his paper on this got rejected. Subsequent papers got accepted, of course, but his paper on this original one got rejected. And it wasn't until 30 years later that finally the first SIAM journal Optimization, in its first issue, agreed to finally publish this breakthrough paper, which was not actually published for 30 years. So if you're ever worried about your own work not getting published for a while, people just don't appreciate it, just remember this has happened in the past. This is not a unique situation here. David was also sort of a remarkable guy. He was and this is entirely separate, but he was also a peace activist. He was responsible, I think, for organizing he didn't do it himself, but he was one of the organizers of a break-in to some FBI headquarters to get documents that revealed illegal surveillance around the time of the Vietnam War. So he's really sort of amazing person, in addition to being, of course, a brilliant mathematician. And it's always sort of interesting to see the history behind both the people and these actual developments of the algorithms. Okay, so what is this method he developed, or what are the methods that he developed and then built upon? So the basic template of quasi-Newton method is actually very similar to what we've seen already for Newton's method, et cetera, with one key difference, though. So what we're going to do is we're going to start with some initial points and then some initial estimate of our B matrix, right? Our approximate kind of Hessian in some sense. And that could be, the B0, by the way, could just be like the identity or something simple. Don't worry about the exact form of that. The first one's usually pretty simple. What we're going to do then is we're going to solve our update, given that B, to find our update for x delta x k minus 1, like with our normal quasi-Newton equation there. Then we update, of course, xk by taking a step in that direction. And then somehow we compute our next estimate of our B matrix based upon our previous one and based upon what we saw in our steps. Okay? And that's the basic, I mean, I haven't filled in any details yet, but that's the outline for how quasi-Newton methods actually work. Now, different quasi-Newton methods, they implement step 3 differently. That's their big difference, is that some of them can find different ways of implementing this update to B. And we'll go over a few possible updates to B in this course. Now, the basic idea here is that B k minus 1, our previous estimate of the Hessian, well, again, I shouldn't say estimate of the Hessian. It's kind of like some sort of approximation of the Hessian. But our previous one, it already contains some information about the Hessian. So in some sense, we should be able to use it to compute our next update. And this equation here is actually the key equation about the property we want to preserve of this approximation B. So actually, so this is the equation here. I'm going to write it again on the next slide using just pluses and normal x's instead of this, but I'm just going to rewrite this equation here in this form here. So this is called the secant equation. And it says that the gradient of f at sort of, the next iterate x plus is equal to the gradient at the previous iterate plus this matrix B times x plus minus x. Okay? This is called the secant equation, and it actually is sort of the foundation for quasi-Newton methods. So I'm going to try to give you some insight into this equation here, which is not on the slides, but I just want to sort of draw this out graphically here to give some insight into this. So the starting point here is actually going to be Newton's method for just root finding. So hopefully, in calculus in high school or in early college, you learned about Newton's method for root finding here. So, which is, of course, a simpler case of the Newton's method you learned in this class. So Newton's method is just going to be the 1D case for root finding. Okay, but the idea of Newton's method is the following. So suppose we have our x-axis here, and suppose we have some function. I'll draw that in green. So suppose we have some function. All right, so what Newton's method does is it says, I'm going to have my iterate at some time here. All right, so at some point in time, k, I have my iterate here. So call this here xk. And I'm going to form an approximation to this function by drawing the linear approximation at this point. So I'm going to draw kind of this approximation here. And what I'm going to do with Newton's method is I'm going to see what this approximation crosses the x-axis and then pick this as my next iterate, right? So this will be my next iterate here. Oops, k plus 1. And just to sort of make everything final here, the equation of this line would be to say that sort of, my approximation for f would be equal to the real f evaluated at xk plus the derivative of x evaluated at xk times x minus xk. Right? That's the equation of this line here. Right? And you solve it. Newton's method says I solve that, set that equal to 0, and that's my next iterate. Right? But the question, and the motivation for what's called the secant method is that what if we don't know what the Hessian is? What if we can't compute, sorry, and I guess it would be the gradient here, the derivative here, because of course for Newton's method for optimization, we're finding a 0 of the gradient, so like we take one more derivative here of everything. But the normal secant method, which is kind of the motivation for the secant equation here, again in 1D and applied to root finding, is if we have the same thing here, so suppose we have the same thing, we now have our function. And if we don't have the Hessian, say at this point here, right? If we can't compute the, sorry, not the Hessian, I keep saying that for, if we can't compute for whatever reason the derivative of that point there, we can approximate it. So this is our point, xk. We can approximate it by looking back at our last iterate, say xk plus xk minus 1, and just forming the line between these two things. Okay. That's kind of like an approximation to the gradient at this point here. I'm sure this should probably be on top of this line here. My drawing is not perfect here. But the functional form of this would be to say, my approximation for x, is equal to x evaluated at xk plus the slope between those two lines, right? So that would be xfk minus fx k minus 1 divided by xk minus xk minus 1 times, again, my sort of how far I am from this point here. Oops, x minus xk. You can see that? Yeah. Okay. And that would be my approximation to this system here. And this is sort of taking the role of b in our equations we have here. Right? So that's a simple idea, is that what b is b is some kind of notion of an approximation to the Hessian. In our case, because again, we're talking about not computing zeros of a function, but computing zeros of its derivative, which means the analogous situation here is you sort of take second derivatives of everything here. Now, the problem with the multivariate case, though, so we're interested in multivariate a multivariate analogy of this equation, is that you can't use just the past iterate anymore, right? There aren't enough points to sort of tell you what that line should be uniquely if it's a plane with just 2 points, right? So we need some sort of generalization of that, and that's exactly what this equation actually is. That's exactly what the secant equation is there. It's a generalization of this sort of notion of drawing 2 lines from the past, one from the previous iterate to the most recent iterate, to the multidimensional case. Yeah, there's a question there. Yeah, so B is, don't worry about that too much, just pick the identity to initialize B. It can really be anything, but we're going to start with something, and then each that's, can be anything actually, and then each step we're going to update it, and then hopefully over time we get more, a better and better approximation of the Hessian as we go. Yeah. So the way we're going to write this all is we're going to write this as the secant equation. Even that's a little bit too much for us because we're going to have a lot of these terms. You're going to see a lot of them in a second. A lot of S's and Y's you're going to see in this lecture. So we're going to write this secant equation as saying that my next b times s should equal y, where s here is the difference between the iterates, and y is the difference in the gradients. All right? And so if anything is sort of not quite making sense with notation, you might want to come back to this definition in this slide again. Just those 2 terms, you'll see them a lot. Just remember, this is S is the difference of iterates, and Y is the difference in gradients. Right? And of course, this is just a simple rewrite of that expression there. Okay, so that's the sort of basic intuition of the quasi-Newton approach. And there are, of course, however, many B's that will satisfy that, right? B is a matrix. The other two are vectors. So you have, n equations, but you have n squared possible things you can select in B. And so what we want is we want B to have a few extra properties. So first, it should be symmetric, right? The Hessian's symmetric, so we should approximate it with a symmetric matrix. And also, B should be, in some sense, kind of close to B. B plus should be kind of close to B. We don't want to move too far away, take too big a jump after seeing only one point. And finally, we should have positive definiteness preserved for this update. So in other words, if B is positive definite, then so should B plus also be positive definite. The Hessian for a strictly convex function will also be positive definite. And so we want an analogous property for this other matrix we're using here. We want it to be positive definite. So that's the sort of basic outline. So this brings us to the first method that we could ostensibly use to actually attain this sort of kind of update, which is called the SR1 method. And I'm going to write it. I'm saying it here mainly for for educational purposes. No one uses SR1 for a reason I'll talk about in a second. Namely, actually does not preserve this property. Doesn't preserve positive definiteness. So no one uses this, but it's still instructive about how these things actually work. So the idea is quite simple. The idea is let's try a rank 1 update to B. So let's try to, if we have B, let's set B plus to be equal to, so I'll talk about now, SR1. That stands for symmetric rank 1 update. So let's set B plus to be equal to B plus A U transpose for some vector U. And A here is a scalar. I could wrap A into U itself, but it actually is a little bit just easier notationally to have a separate multiplier, which for reason you'll see in a second, on U. So I'm going to write it this way. Okay, so now let's sort of write the secant equation with this. So the secant equation would say that B plus times S equals Y. So that means that B S plus A U transpose S is equal to Y. Right? And so I'm going to write this a little differently. I'm going to write this as here. This is just a scalar, and so is this. So I'm going to write this equivalently as saying that A U transpose S, put parentheses around it, just remember that that's just a scalar, it's a scalar value there, times U equals Y minus BS. Okay? So that's our equation that we have that's implied by the rank 1 update plus the secant equation implies this form here. Now, this is n different equations here, right? And we're picking n variables here. So it's not too hard to see that in order for this to be possible to be satisfied, you have to pick U, of course, in the direction. U has to be some scale multiple of Y minus BS, right, for this to work. So then for simplicity, let's just set U equal to Y minus B of S. B times S. And then this term here, it should be equal to 1. So we have this equals that, and then we have A U transpose S equals 1, which means that A equals 1 over U transpose S, which means that this equals 1 over Y minus BS transpose S. So that defines what both A and U is. And you can sort of see now why I kept A separate. It's a little easier to just define U as that vector there and then solve for A to find the scaling of it. That's all we're doing there, though. So now we just, and I won't write this, but we just take that solution, then we just plug it in to this, and hopefully it's pretty obvious. It's just, this is U, so it's U transpose divided by, times A, which is divided by this thing. That is our update. And this thing here is then the SR1 update. So there are a few nice things about this. One of the nice things about this is that, you know, if we did this, if we just sort of implemented this as you saw there, right? If we just sort of implemented it like this and updated B this way and then ran the Quasi-Newton template as we saw a few slides ago, we still have to solve for the inverse every time of S, right? So let's just solve the linear system involving, sorry, the inverse of B. We still have to solve every time a linear system involving B, and that would still be n cubed time. So that doesn't seem to be a great, yes, we can update it, that's all nice, but what's the real benefit if you can't actually solve it any faster? So because of this, what we're actually going to do is, in practice, we wouldn't actually use this equation. We wouldn't really use this update equation. Instead, we would actually directly maintain the inverse of B, which is what we're going to call through this lecture here C. So instead of maintaining B, we're going to maintain C, which is the inverse of B. And we're going to do it, and the way we're going to do that is we're going to use what's called the Sherman-Morrison formula. This is a formula that lets you perform rank 1 updates to a matrix directly in the inverse, right? And so the formula says that if I have some matrix A, and I want to add a small low-rank update to A and take the inverse of that, I can do this equivalently by just taking the inverse of A and then adding this specific form of another low-rank update to the inverse. Right? So at a high level, a rank 1 update on a matrix inverted means a rank 1 update to the inverse as well. Okay. And in this case, of course, you know, B takes the place of A there, and C takes the place of A inverse. So the idea, we're just going to apply the Sherman-Morrison formula. You know, so our update to B, right, was B plus equals B plus. It was this A, U, U transpose. So in this sort of a notation here, you know, U can say take the place of A, whatever, utility, A, U, and our, you know, V here takes the place of U transpose, or U. And so B plus U V transpose inverse would equal, of course, you know, B inverse minus B inverse U V transpose B inverse over 1 plus V transpose B inverse U. And of course, this is just going to be, you know, C everywhere where I see B inverse before. So I have my previous, so this thing here becomes the next inverse. And here, wherever I see B inverse, I just substitute in the previous thing, C, and I actually won't go through what these actually are, but it's just on the slide there. 1 plus C. Okay, so basically this is an update directly for C, and it just has this form here. Right? And you can write everything in terms of that. Now, this is nice now, because now every step of the computation of the Quasi-Newton method becomes order n squared. So this update here is a rank 1 update to a n by n matrix. So this update here is order n squared. Multiplying, you know, C plus times the gradient of f at xk, that's also going to be an order n operation, order n squared operation. And so every step of the Quasi-Newton, and of course, you know, updating the vector itself is just order n. So maybe going back a few slides here. Oops, here's what I want. Every step here, the first step is n squared, the second step is order n, and the third step is n squared. So every step of the method is n squared, and so we now have an n squared approximation to Newton's method, or something like Newton's method. Okay, so what's the problem? The problem is that this update you can show and there's no reason to think it would. In fact, you have to prove it in the other case that it does, in fact. This update, there's no reason to believe, in fact, it does not, preserve positive definiteness. So what can happen is that even though you have, say, a strictly convex function even, as you're going along, your estimate b can actually start to become either indefinite or maybe even rank deficient. And so all of a sudden, at some point, you really don't have the curvature you want to approximate when you're optimizing a convex function. Right, so this is a bad thing. It basically makes it go unstable. And the solution, once you've gone, once the matrix here becomes indefinite, so it has some negative eigenvalues, you really can't say anything about how well it's going to work. So these things, that doesn't work very well, doesn't converge, has all these problems. Okay, so that didn't work. It was a great idea, but it didn't work, unfortunately. So what's the next thing we try? Well, a rank 1 update didn't work. So let's just keep marching along and try a rank 2 update instead. Hopefully that'll work, right? It turns out it does work, actually, maybe amazingly enough. So instead of updating B with a rank 1 update, we're going to update B with a rank 2 update. So this equals B plus some term A, U transpose, plus some term B, V transpose. So now we're going to update, we're going to perform a symmetric, again, rank 2 update on B, and we're going to see what happens. Turns out it will work kind of amazingly. All right, so I'm going to write it like this. So again, we take that update, we apply the secant equation, i.e. we multiply this whole thing by s, and set it equal, and have that have to be equal to y. And what we get there is the following. So using the same kind of groupings that I had before, we have y minus, I'm going to write it like this, bs. No, that looks exactly the same for this. The colors aren't coming through. Let's try it again. All right, so y minus bs is going to equal equals a u transpose plus b v transpose. Okay. I'll go. Sorry, whoops. There's an s there. Actually, let me write it like this. Hang on. One more thing. This is times s on both sides, but let me just write it like this, like it is there. Y minus. I'll do the colors in a second again. I want to show, but equals again sort of in parentheses a u transpose s times u plus b v transpose s times v. So all I'm going to do here is I'm going to set u to be equal to y and v to be equal to, maybe this is a different color here, v to be equal to this thing. Okay, so this is somewhat arbitrary, right? Because I could pick it to be any kind of mixture of these two things. But I believe what happens if you do that is you just get kind of a rotated version of this thing. You get a very similar form to the update, even if you do this. So this is what our choice is going to be. I'm going to set v to be equal to bs and y to be equal to u, or u to be equal to y and v to be equal to bs. That of course means that we have things like well, we need now a u transpose s has to be equal to 1. This will imply that a equals 1 over u transpose s, which equals 1 over y transpose s. And b, v transpose s equals negative 1, which will imply that b equals negative 1 over v transpose s, which equals negative 1 over s transpose bs. B is symmetric, remember, so I don't need to worry about transposing b. Okay, so if I plug these two settings now in, I get this update here. So the v's actually become this term. It's bs times s transpose b over s transpose times b times s, but negated because we have a negative 1 in front of b here. And then the a term becomes this term in the same way. Right? And this is called the Broyden-Fletcher-Goldfarb-Shano update. They didn't really work together, but they all like found similar. Some of them worked together, and some of them found it simultaneously in the same way. So it doesn't mean anything algorithmically. It's just the names of the people that developed it, and it's one of like the most common algorithmic names that mean nothing, but just people's names that happen to invent it. This is called the BFGS update, and it actually ends up being one of sort of the workhorses of convex optimization. Okay, so let's dig into a little bit now. So this is the update, but again, if you remember, before what we had to do is we couldn't just directly update B in this way and maintain B in this way. What we actually want to do is we want to maintain the inverse of B, which is C. And what we can do, fortunately though, is the exact same thing we did before, we can now do again. The difference is we need a slightly more complex formula here. So whereas before we had this Sherman-Morrison formula, which is for the formula for a rank 1 update of an inverse, now we have a rank 2 update of the inverse, right? We want to update kind of we want to take the matrix B, perform a rank 2 update, but maintain its inverse after we do that. Fortunately, there's a simple generalization of Sherman-Morrison, which is called the Woodbury formula, or sometimes the Woodbury-Sherman-Morrison lemma, and things like this. And it basically gives the generalization of the Sherman-Morrison formula for a higher rank update to the inverse. So the idea here is that if you have the inverse, that's an inverse in n by n dimensional space, where here the update u times d times v is, say, in our case, rank 2. And this gives an expression for it, and the only really important part to note here is that thing that matrix in the middle, the D inverse plus V A inverse times U, all inverted, that's going to be, in our case, a 2 by 2 matrix that we're inverting. And just you can see that if you just look at the sizes here. In our case, U is going to be B times S and then Y, and D is going to be those two terms. That's just how you make that rank 2 update on the previous slide written in this form here. And so if you just now do some matrix algebra, and I won't bother with this, it ends up involving like you form this rank, you form this 2 by 2 matrix, which is that D inverse plus VA inverse U matrix. You analytically invert it using the determinant formula for a 2 by 2 inverse. And after a little bit of algebra, what pops out is this. This formula here, which gives us the update, after some time, gives us the update for how we maintain a rank 2 update to the inverse of B, C. So this is actually what people typically call the BFGS update, because this is how you really compute it in practice. It is, our next inverse is equal to some update on the inverse here times the previous one, YS transpose, plus SS transpose Y transpose S. Okay? So that's the form you typically see BFGS written in as an update. Again, because in practice, you don't ever maintain B, you maintain its inverse C. Let's see, actually, if I want to get to this. Okay, so this is, yeah. So the next point I want to make is sort of this important point, which is that somewhat, maybe surprisingly, given that SR1 didn't do this, but what's very nice about this rank 2 update, kind of magically, is that this update now preserves positive definiteness of B, right? And what that means is, and we're actually going to show that it produces positive definiteness of C, because if a matrix is positive definite, its inverse is also positive definite. But this update that I've written here, actually, if C is positive definite, so strictly positive definite, right, has eigenvalues all greater than 0, and actually, the other condition that has to be that this term here has to also be greater than 0. If it's less than 0 or equal to 0, obviously things will blow up with this. But just to be clear, again, that condition, this term here, that's equal to, again, y is the difference in gradients, s is the difference in iterates. This condition here is actually guaranteed by, say, strict convexity of the function. That's actually one of the conditions you have of convexity. So it's not surprising, right? I mean, Newton's method can have an indefinite Hessian if you apply it to a non-convex function. But for a, say, a strictly convex function, this thing will always be positive, and so this thing is that condition will hold. But under those two conditions, so that y transpose times s is positive, strictly positive, and c is strictly positive definite, then the next iterate, c plus, is also strictly positive definite. And the way to say, and that's actually not completely obvious, though, I should say. You could say that, okay, this term is clearly positive definite because it's, a positive matrix times two things. Positive semi-definite, really. Can't quite say for sure that it's positive definite. This term here is also clearly positive semi-definite. But why, couldn't it be positive? Couldn't there be a zero eigenvalue that sneaks in there somewhere? And there actually can't be. And the way to see that is actually just multiply some vector x by this thing. So if you multiply some vector x on both sides by this thing, remember the condition of positive definiteness says that this thing is 0 if and only if x is 0. And so if you multiply this out, what you see is that you have these two terms here. Now this term can only be 0 if s transpose times x is 0, right? So this one's only 0 if s transpose times x is 0. And if s transpose times x is 0, then this term here, these two terms here are also 0. So this term is just x transpose c times x. And so that one can only be 0 then if x is 0. So the high level is that there's these two terms, and they cannot both be 0 unless x is equal to 0. Otherwise, one's strictly positive, and that's exactly the definition of a positive definite matrix. So this is why it preserves positive definiteness in these updates. And that's a very nice property, and that's why BFGS actually becomes kind of the standard approach, really, to quasi-Newton methods, or has become the standard of quasi-Newton methods. Any questions there? We've sort of gone through a lot, but it's all really quite straightforward, actually, in some ways. It all kind of falls out of the secant equation once you require these updates, either rank 1 or rank 2 updates. And so it's actually, the algorithm, though it seems complex because it has lots, just wait. We're going to give it another 4 minutes. It's even more complex than this. But it's all actually follows pretty naturally from kind of basic linear algebra. So any questions now? Yeah.
Is the only reason you would use primal dual or barrier methods because you can impose constraints?
So why would you use primal dual or barrier method above this? Yeah. So right. So this is great. This is actually quite different in a lot of ways. Yes. So it is not easy to apply this to constrained cases. There are quasi-Newton methods that try to solve the KKT conditions for a constrained problem. Those have some issues, though. Those are a little tricky because the barrier method, or the central path along with the quasi-Newton update gets things a little bit nasty. But yes, I think if you want to solve sort of a large unconstrained problem, this Newton method you might use this because it's simpler, but really it's the comparison of node is not interior point methods versus this. It's Newton's method versus quasi-Newton methods. And at a high level, other than the added complexity, which is a little bit, they are somewhat superior to Newton's method, yes. It is a little bit hard, though, to apply them to constrained cases. So, for example, primal dual interior point methods that try to use quasi-Newton solvers within them are by no means as mature technology as normal quasi-Newton solvers. As normal interior point solvers. Or quasi-Newton solvers, for that matter. Anything else? Okay, now, historically, I do want to mention one other algorithm, which is actually the one that William Davidson came up with when he was not able to publish it for several years. I don't know, and this is called the DFP update. It works kind of actually similar to BFGS, but for some reason it's become a little less popular. I'm not really sure why, but BFGS is kind of the standard these days of what people actually use. DFP has somewhat fallen out of favor. I'm not quite sure why, but just it's worth knowing this for both historical reasons because it predates BFGS. This was the one that this was the original, in some sense, quasi-Newton method. After SR1, but the first one that really worked. It also has the same property, the same benefits as BFGS. So like BFGS, it preserves positive definiteness of the Hessian. Really, for the of the Hessian approximation B, has n squared computation. So all the same, and it has the same convergence. Actually, we'll see in a second. But for whatever reason, it's a little less in favor. However, it's still kind of interesting to know about. So the idea of DFP is really exactly the same as BFGS. We're going to do a rank 2 update. But this time, we're actually going to apply the rank 2 update directly to the inverse itself. So instead of having our rank 2 update on B and then deriving an equation after some linear algebra for the update to the inverse, we're just going to kind of sidestep all that and directly, given that we're going to compute the inverse anyway, C, that's what we're maintaining, let's just do directly a rank 2 update on the matrix C. And if you do the exact same tricks as before, use the sort of the inverse form of the secant equation, right? Because C is what you have before. You get something that looks very much like the normal BFGS update on B, but updating C, the inverse, directly instead. And that's this equation right here called the, again, these things all have the names of people, not of actual methods. So this is called the DFP update for Davidson, Fletcher, and Powell. The F is, there's no people in common, right? Because the F there is, no, Fletcher is on both, right? Okay. Fletcher is, yeah, he got his name on both of these, so. But like I say, it's, it's something that kind of seems simpler because we're maintaining C anyway. Let's just directly update C. That seems a lot, that seems like less of a headache than this equation here. But it's just not as common anymore. There must be a reason for that. I assume that there's some situations where it doesn't quite work as well, but I honestly don't quite know what those are. I just use BFGS or LBFGS because that's what everyone uses. Okay, so the last thing I'll say is that it turns out that oh, and by the way, for the same for DFP, you can use the exact same logic actually to prove that it maintains positive definiteness of the updates, because this form implies essentially exactly the same form of the inverse of C, which is B. So this actually implies a very similar update to this thing here for B, and then you apply all the same logic to B directly to show that it maintains positive definiteness. So it's the same, it's really the exact same proof. It's a very, very similar method. They just have this sort of, opposite sense in which they directly update B, do they directly update B inverse with this rank 2 update. So the last thing I'll say is that it turns out actually all these methods are special cases of something called the Broyden class. And the Broyden class really is just, it seems silly when you write it this way, but it actually is a little bit more interesting than this. So the Broyden class says, well, we want to generalize BFGS and DFP. So we're going to form the convex combination of these things, very cleverly. Therefore, it generalizes both of them by definition. I guess Broyden wanted his name on maybe DFP also, so he had to generalize that as well. The only thing else that's kind of interesting here is that, of course, you can define an algorithm as a convex combination between two things, and then it generalizes both of these. The interesting thing, actually, though, is this is also a specific choice here of phi, which is the interpolating factor. This actually corresponds to the SR1 update. So it turns out you actually can also recover the SR1 update in this class, this thing called the Broyden class, but no one uses anything but BFGS anyway, so it's mainly just there for sort of completeness, saying that all these three things actually can be achieved by the same algorithm, by the same kind of general algorithm there. And the update actually has this sort of form. It looks a lot like BFGS, but just with an additional term here that depends on phi. Okay. Any questions now? Yeah.
Any insight on how it chooses the next point in the secant equation update, or is it more like kind of random how they proceed, like making these? You
mean this Broyden class here? I see it just as like someone said, well, we have to be more general, so we're going to interpolate between these two things. I'm sure there was more to it than that. I guess it would be kind of a rank 3 update, but for the right choices of these things, terms cancel to make it either rank 1 or rank 2. That's the only insight I really have into it. I don't have a good insight into that because it could be up to a rank 3 update, and is that really useful or not? I'm not really sure.
In terms of like how it looks in the space, in terms of how they choose updates, is that like more intuition, or is it also just more like?
Well, so the intuition behind both. So the question was about the intuition behind the choice of the update for both DFP and BFGS. The intuition I get for them is they constrain themselves to a rank 2 update on B or on B inverse. And I mean, and to be clear, actually, like a rank 2 update on B implies a rank 2 update on B inverse, but it's a little more natural, the form of rank 2 update you get in the original space than in the inverse space. So the intuition I have really of how it picks the next one is just this for DFP, for example. So it is just I want C plus to be close to C, and the way I'm going to make it close to C is I'm going to pick it to be a rank 2 update to C, and that's the extent of the intuition that I really have about it. Yeah.
Is the strictly convex assumption a strong one in this case?
Well, so in some sense, the question was, is the strictly convex assumption a strong one? So in some sense, you kind of expect that, right? So if you apply Newton's method to a function that is not convex, you will have an indefinite Hessian, and it will not work if you have to do other things to make it work. So it's not surprising that an approximation to Newton's method also requires strictly convex functions to be strictly positive definite. Otherwise, it would be kind of weird, to be honest. Otherwise, like what would it be computing otherwise? I don't really know. So in some sense, it is a strong assumption, of course, because convexity is always a strong assumption. But since this is a class on convex optimization, in our case, hopefully it isn't too bad. We can still, get along okay with, even with this assumption. Okay, so we have one slide now on convergence analysis. And actually, I'm not going to prove anything here. I just want to tell you what the result is for convergence for these quasi-Newton methods. So quasi-Newton methods attain what's called superlinear convergence. So you've seen linear convergence before for gradient descent, and you've seen quadratic convergence for Newton's method. What that means really, for the case of linear convergence, which is what gradient descent has, says that the difference between the iterates and the optimum decreases by some multiple each time. So say you have C xk minus 1 minus x star. So this is linear convergence, right? It means that the difference between the optimal is sort of decreasing by measuring the two norms, decreasing by some linear factor each time. Whereas quadratic convergence, this is what Newton's method has, at least locally when you're close to the optimum, says that this thing is less than this. And C, of course, embeds constants like the Lipschitz function, like the Lipschitz constant, like the minimum eigenvalue of the Hessian, things like that. So those are both the little m, the L, the little m, and the big M coefficients. But I'm just going to write it as C for now. Quadratic convergence says this thing decreases with this norm squared. So that means that if this thing is small, then this next one is small squared, which is really small. So that goes to 0 really, really fast. And superlinear, which is what BFGS has, or quasi-Newton methods have in general, looks kind of like linear here. So it's going to say that this minus x star some C times k minus 1 minus x. But this multiple changes each time, and ck goes to 0 eventually in the limit, as k goes to infinity, I should say. So this is sort of I'm not saying how quickly it goes to 0 or anything like that. I'm just saying that it goes to 0 eventually. So eventually this is better than linear, right? Because linear says this happens with some fixed constant. So eventually this becomes better than linear. It's not saying it's quadratic, right? It's not saying that it actually achieves quadratic performance. It's just saying that eventually it's doing better than any linear rate would be doing, right? And that's the kind of convergence you get for quasi-Newton methods. We're not going to get to the proof here at all. It's not that bad. It's just sort of looking at the iterates of these things and doing a lot of analysis, actually a lot like the analysis for Newton's method, but it's still something it's not worth going through. It's just mainly the fact of it more than anything else. One thing I do want to highlight, though, and I'll mention this again when we get to it, but limited memory quasi-Newton methods are not actually, they do not have this property. So they're not actually quasi-Newton methods in this sense. They just seem to work better than gradient descent, so we kind of like them. They're similar to quasi-Newton methods, but LBFGS, for example, if you've heard of that method before, that does not have this property. It will only have linear conversions. So be careful. You really need the real quasi-Newton, the full quasi-Newton, n squared update typically to get these kind of properties. Okay, let's see where we are with time. All right, we have about 15 minutes left. Okay, so here's a plot. This is, I guess, an example from Lied and Vandenberg's notes, and it shows here for some, smooth differentiable function. It's a twice differentiable function here. It shows minimizing it here. So it's a linear term plus a sum of log terms where the dimensionality of x is 100, and there are 500 terms in that sum. And this is the convergence of Newton's method. So with about 12 iterations, it goes to 0. And here's the convergence of BFGS. So it actually has a very similar shape to it. So even though we didn't prove quadratic convergence, it actually looks very similar. It looks kind of like quadratic convergence. And it definitely is better than linear convergence. But the important thing here is that the Newton updates, each one of these updates is n cubed. So it's 100 cubed. Whereas each one of these updates is 100 squared, n squared. But we do not require 100 times more updates here to get as good performance here as we do here. So actually, it only requires about 10 times more updates than we needed here, which is substantially less than n cubed. So in this case, clearly from a pure computational standpoint, we are ignoring constant terms, at least asymptotically, right? We are doing better if we use a quasi-Newton method than Newton's method. And this seems to be sort of a pattern. If you have something even remotely large scale, you seem to do better in terms of computation applying a quasi-Newton method than just applying Newton's method. All right. So the last main thing I want to say is to talk about, lead up at least, to limited memory quasi-Newton methods, which are actually also kind of a workhorse of modern convex optimization. And the way I'm going to start is by talking about implicit form quasi-Newton. Right? So the basic idea here is that if n is really big, maybe even quasi-Newton methods are just not good enough, right? Even that n squared term is too big. And actually, that isn't that hard to imagine either, right? So if n's millions, then just forming the matrix C would be a million by million matrix. You probably couldn't store it in memory anywhere, right? So you can't even do that. You can't even form the matrix. Whereas gradient descent in a million parameters, we do all the time, right? So there's something missing, for really large scale optimization here. So the way that we're going to sort of achieve this is we're going to actually consider kind of an iterative form of the BFGS updates. So I mean, if n is a million, right, then probably after a million or after k updates, and with maybe k much less than a million, right? So say after 500 updates. We don't need to actually compute C itself. We can just look at what C was originally and kind of store all those rank 2 updates that we applied to it in the past. Okay? So that's the basic idea of this implicit form, is that if our number of steps is much less than the actual dimensionality of the matrix C, we shouldn't actually form the matrix C. We should just sort of keep around everything we will use to form it and sort of implicitly compute the solutions that we need using just the whole history of things. And so what we're going to do is we're going to actually maintain all the previous y's and s's. Okay, so we're going to maintain every single previous difference of gradients and difference of iterates. And we're going to compute solutions to the equation C times G. Remember, that's B inverse times G. That's our quasi-Newton update. We're going to compute them recursively. And I'll give the actual algorithm in a second. It's based on this really simple kind of observation that if this is our update to C+, we can write C plus times G, that's the thing we want to solve eventually, as a function of some other things that involve basically terms involving S and Y, and then C, our previous matrix, times some other terms. All right, so basically we can represent multiplication by C plus by multiplications by C. All right, and of course we can then recurse in that. So we can represent C by multiplications of C, one time ago, et cetera, all the way back to when we started at C0. All right, and that's the basic idea of this implicit form quasi-Newton. This, by the way, just falls out kind of naturally, by definitions. If you just multiply by G and just substitute in these conditions here, you have kind of a simple update for simple form for the update here. So without getting into too much detail here, because I don't want to derive this necessarily, you have to sort of trust me this is in fact the right algorithm for it. It turns out we can compute C plus times G for sort of any C, however many steps you took, by 2 loops, sort of like a forward and a backward pass almost, involving each one k steps. And this is after assuming we have taken k steps so far in the algorithm. So let me just sort of write the summary of this. So if we have the explicit form of a quasi-Newton method, it requires n squared memory because you have to store the entire C matrix. It also requires n squared time per update. Right? Because you have to update it every time. So if you take k steps, it'll be, I'll just write it like this, k n squared time. Right? 'Cause to update it each time you do k work. Whereas the implicit form, if you just run this algorithm, each step here, so first of all, so let's look at the implicit form here. The memory now, so you have to store all the previous y's and s's. So you do have to store that. So it's going to be k times n memory, where k is our iteration number. Right? And each update you do is going to be k times n time, because we're in this loop. So each time you update things, it's going to be k times n computation too, because each of these steps is order n. They're just basically inner products at each step, forming these, I should say, these intermediate factors here, p, alpha, beta, s. Actually, that's how much time I have. I don't really have time to go through this. I might just want to do a little aside here. So this is a really simple form here. I just want to emphasize this is quite simple. So the way you get this thing, by the way, is just to take C plus with a definition and multiply it by G. So if I have I minus, I always forget the order of the things, S y transpose over y transpose S, C I minus S, that was y, S transpose over y transpose S times G. plus S transpose over Y transpose S times G. It really just sort of follows by sort of taking definitions here. So by the following definitions. So this term here, like this term here, we just call alpha. That is S transpose G times that. And if you sort of simplify things, so now there'll like be one there too. So this is going to equal I minus S Y transpose S times C, and then it is G minus, this would be Y times another alpha there, so Y times alpha G plus alpha S, etc. And if you sort of, oops, this is times alpha Y here. And you basically just go through this, and it's sort of just definitional. How do you get that? So you can go through these equations sort of in the past, but the point is all these terms here are just order n to compute, and then or they involve this term sort of multiplication with the previous, and you can kind of go through it recursively to do that. All that really is saying is that leads to this algorithm here. I don't want to dwell on that too much, but I just want to sort of give some hint about how that actually comes about. So the implicit form requires kn memory, because you have to maintain every single y and s vector up to the current point, and it will require well, how much? What will the time complexity be? Actually, ask questions more in class. But what will the time complexity be of the for the entire run up to time k, say up to iterate k? Sorry, we'll say that again. Kn plus n squared. Kn plus n squared. Where would you get the n squared term? We're trying to avoid the n squared term, actually. 2kn? Yeah. So each iteration is order kn, but then you have to do k of them to get up to point to your final iterate. So the final, and I counted k in there in this one too. So the equivalent thing will be k squared n time. And of course, if k is less than n, so if you don't take as many updates as the size of your parameters, which you might not if you have a million parameters, this is better, right? This is going to be better to just not ever store your C matrix exactly, but just kind of store it implicitly by essentially reforming every computation you need to get to that point whenever you want to multiply it by something. And that's the basic idea, okay? But now, okay, yes. This is like time total. This is like total time to get up to step k of the entire algorithm.
Yeah, I guess what I'm saying is like on k equals 1, you only step through those four loops like one time.
One time, yeah.
Yeah, so k doesn't actually multiply out as k squared. It's like a
Well, it's like a double for loop, so it is order k squared. It's like k times k minus 1, k plus 1 over 2 or something like that, right? But it's order k squared. Yeah.
For the previous picture from the Vanderburg example, like
Yeah.
k was bigger than n when it converged.
Yeah, it's a good point, right? So it's probably a bad idea here, because here actually k is bigger. Modulo like constant time, right? Which is is this a little bit bigger here maybe than maybe like the actual factor is a little smaller. But yeah, here you would probably just go with a normal one. And actually, to be honest, people don't really use the implicit form for normal BFGS. I'm actually introducing it largely because it leads to the next thing, which I'm going to talk about. Because the reality is, while it's great, if you really want exact convergence, you oftentimes do need to actually take at least n steps with whatever your dimension is. I mean, this is sort of just sort of empirical here, but it is the case actually for quasi-Newton. You oftentimes do need more than just n steps to converge to at least numerical precision. So if you really want numerical precision here, oops, I've frozen my document cam. That's too bad. Huh. Maybe I'll just press it again. Can I? Let's see if that comes back. Whether you would really want to use this in practice for implicit form for exact BFGS is, I think, not completely clear, to be honest. But what actually this leads to is the limited memory form of BFGS. This kind of raises an obvious question, right? What if instead of going all the way back, so in some sense, BFGS is maintaining this matrix C, and every time we're updating it, we're kind of bringing in a little bit more information. And as this kind of makes clear, our final form of C uses information from all the way back to the start of time up to the current point, right? We've updated it that many times. And that can be a lot, right? K here can be pretty big if you take K total steps. Maybe it has to be bigger than N at the end. So what this really motivates, actually, is what's called limited memory BFGS, or LBFGS. The L is not a person. The L is limited memory in this name. The rest are people. But LBFGS is this acronym. It has no, you can't pronounce that either. You can't call it LBFGS or something like that. So everyone says LBFGS is this long number of syllables that we all talk about whenever we mention optimization, because it actually is one of the fastest algorithms for optimizing smooth convex functions. And the idea is actually really simple. The idea is we're not going to go back to 0 in our iterations here. We're only going to go back m steps. So here m is the important thing here. Rather than going for I equals k minus 1 to 0, we're going to k minus m. So we're basically looking only at the m most recent steps to compute kind of our current iterate C. Right, other than that, it's actually identical to the previous slide. It's just the same exact equations here, so it's the same exact form of the BFGS update. We're just truncating it, so both in the backward iteration and the forward iteration, we are truncating it at m steps. Now, you have to sort of course, just like we have to pick what C0 or what B0 was, you have to pick what your C approximation is, k m steps ago, which is not going to be the true C matrix you would have from a quasi-Newton method. But it is, typically pick things like the identity here. And while some more sophisticated choices exist, this is sort of pretty common. And well, this all seems kind of like a lot of work to do. The reality is, this method now, LBFGS, so this sort of leads us to an even simpler form, which is limited memory. LBFGS. This one is just OMN memory, where m is just some constant you pick, and O, k, the number of steps you have, k, m, and time. So if we treat m as a constant, this would actually be the exact same complexity as gradient descent. So this is same as gradient descent if m is a constant. So that's nice. For the same work, or m times as much work effectively as gradient descent, we have actually a much more complex algorithm, but one which in practice seems to converge much better than gradient descent. So for really large scale convex optimization problems, these are things like large scale logistic regression and things like this. It actually is the case that oftentimes LBFGS is the state of the art for solving these things. And so this method based upon quasi-Newton, but not actually quasi-Newton, because it does not actually have superlinear convergence. It's a truncation where you lose sort of the nice the nice guarantees of quasi-Newton methods. It still ends up working very well in practice and ends up being a sort of a very compelling algorithm. I am pretty much out of time here. So the last thing I just want to say for 2 minutes is that there do exist stochastic variants of LBFGS. As I think Ryan's probably mentioned, stochastic gradient descent really is kind of the state of the art for a lot of truly large-scale problems. And so for these really, really big problems, it seems like it may be faster to use stochastic variants of this. I won't go into them, but there are some actually pretty recent papers. Like this is a paper by Bird and Nosadal also actually. And the idea is, it's kind of similar to LBFGS, but you only perform an update every few iterations, and you use only a few examples in like a batch to to actually compute your gradient, and they can prove this does things that are, seems to be better than SGD. I guess there's a slide in the next slide. It seems like in some cases you actually can beat SGD, which is still the workhorse for really large scale optimization. But I think that the jury is still out on just how popular and useful these things are going to be. And then finally, there's some references if you're curious to learn more. So next time we're going to discuss proximal Newton methods. I'll still be here on Wednesday, but I'm happy to take some questions offline right now, or I can talk more on Wednesday. Thanks.